That is a Claude agent running a research task, 42 tool calls, 0 human touches, clean completion. In the next 9 minutes, you will learn the 3 patterns that made it possible. Welcome to AI Tech Book. This is the Atlas. Today, autonomous agents letting Claude run unattended. Every developer who ships an autonomous agent eventually finds the same gap. The agent that worked perfectly for 3 minutes runs for 45 and does something you did not expect. Not wrong, exactly. Just unexpected. The kind of thing you would have caught if you were watching. The gap is not the model. It is the architecture. A short run agent and a long run agent use identical code, the same loop, the same tools, the same model. They need different scaffolding because the failure modes are different at scale. 3 patterns close the gap: stop conditions, checkpointing, and self-correction. These are not guardrails you bolt on after it works. They are what make it work at duration, at scale, without someone watching. Session lengths are already growing. The agents running in production today are running longer than they were 6 months ago. Patterns that were good enough for short runs are not good enough anymore. The agentic loop has one job: keep going until stop reason is end turn. That is the right loop for a short run. For a long one, it is a liability because 3 failure modes that are invisible at 5 minutes are inevitable at 45. The first is the infinite loop. The agent keeps calling tools, never reaching the exit condition because no one defined what done actually means. The loop ceiling was never set. It just continues. The second is the context cliff. Every token the agent processes eats into its context window. When the window fills, the history is truncated. The agent loses track of its own work. It starts repeating subtasks it already completed because those subtasks are no longer in its view. The third is the runaway action. The agent, still running with no stop condition, reaches a decision point in the task and makes an irreversible choice nobody explicitly authorized. Not malicious. Just outside the scope anyone thought to guard. These are not edge cases. They are what every long-running autonomous agent eventually hits unless you design for them first. Each failure mode has a corresponding pattern. Stop conditions for the infinite loop. Checkpointing for the context cliff. Self-correction for the runaway action. Start with stop conditions because without them, the other 2 do not matter. There is a stop condition that ships in every tutorial: max turns. It is the right first stop condition. It is not sufficient. Most developers set max turns to 50 or 100 and call it done. The loop cannot exceed 100 iterations. Fine. What that does not tell the agent is, are you finished? Did you actually answer the question? There are 3 classes of stop conditions. Most production systems only implement one. The first is the loop ceiling. Max turns, the hard cap. The loop cannot exceed n iterations. This catches the infinite loop. It does not define done. An agent that hits its ceiling marks the task complete whether it is or not. The second is the success criterion. This is what defines done. The coordinator exits when all items in the checklist are answered, when the output format has been filled in full, when every required subtopic has a substantive finding. Success criteria are not a time frame. They are a contract. A coordinator without one is guessing when to stop. The third is the failure signature, the stuck detector. If the same tool result appears 3 times consecutively, escalate. This catches a specific runaway. The agent is looping successfully. It is not erroring. It is not hitting max turns, but it is not making progress. It found one piece of evidence and it keeps retrieving the same piece. The failure signature breaks the loop and surfaces the problem to the coordinator. Most production agents implement the first. The second is what separates a confident-looking output from a correct one. The third is what catches the loop you did not know you had. Context windows fill. That is not a bug. It is a physics constraint. The question is what happens when they do. Without checkpointing, the answer is restart from 0. 2 hours of work, gone. The new context window has no memory of the old one. With checkpointing, the answer is resume from where the failure occurred. 5 minutes to reload state and continue. The difference is one design decision made before the run starts. Anthropic's own multi-agent research system uses a 200,000 token trigger. When the context window approaches that threshold, the coordinator saves its plan. The current task list, the completed subtasks, the sources gathered, the work still in progress, to memory. Then the context can roll over, and the next call loads the saved state before picking up where it left off. 200,000 tokens is a specific threshold. The pattern is general. Any predictable risk point can be a checkpoint. Before a network-heavy subtask, before a file system write, before a subagent handoff. The principle is the same, save state before the operation that might fail. An agent without checkpointing can technically run for 2 hours. It just cannot survive a 2-hour run. The distinction matters when the run is the work. Every long-running agent will hit a tool failure. The default developer response is to catch the error and swallow it. Do not bother the agent, handle it silently in the wrapper. That is the wrong response. The Anthropic finding is the opposite. Letting the agent know when a tool is failing and letting it adapt works surprisingly well. The difference in output is not subtle. An agent that received a silent error produces a confident answer with an invisible gap. An agent that received a clear error message, 503, database unreachable, can adapt, try a backup source, reframe the query, and mark the subtask explicitly incomplete in its output. Honest incomplete beats confident wrong. Every time. The self-correction loop has 3 steps. First, detect. The tool result carries an error flag and a message. The agent knows the tool failed. Second, adapt. Try the next logical approach, a different source, a restated query, a simpler tool call. Third, escalate. After n failed attempts, surface the problem to the coordinator explicitly. This subtask could not be completed. Here is what I found. Here is what I could not verify. An agent with a self-correction loop produces outputs with explicit confidence levels. Verified, these 5 items. Unverified, this 1 item, database was unreachable during this run. An agent without 1 produces uniform confidence with invisible gaps. The one that surfaces its own uncertainty is the one you can actually trust with a longer run. Most discussions of autonomous agent safety focus on what the agent is allowed to do. The better question is, what is the worst it could accidentally do? That question sets the permission ceiling. 2 principles answer it. The first is minimal footprint. Request only the permissions you need. Avoid storing sensitive information beyond immediate needs. The design test? If this agent handles an ambiguous instruction, it was not designed for what is the worst outcome given its current toolset? That answer is the ceiling. Permissions beyond it are blast radius you have not controlled. The second is prefer reversible. Write to a draft before committing. Create a resource with a delete path. Send to a staging address before the live one. The preference for reversible is not extra caution, it is a recoverability property. A reversible action can be reviewed before it becomes permanent. An irreversible one cannot. 0.8%. That is the share of Claude Code actions found to be irreversible in recent research. Customer emails, payments, destructive rights. The number seems small. Those actions are the ones in every postmortem. Minimal footprint and prefer reversible are not about limiting what the agent can do. They are about making the blast radius of any mistake, the mistake you did not anticipate, contained and recoverable. An agent with minimal permissions and reversible defaults can be given more autonomy safely. Because when something goes wrong, the damage is bounded. The naive autonomous agent and the survivable one use the same model, the same tools, the same while loop. They differ in 4 design decisions made before the first run. The naive agent has a loop ceiling and no success criterion. It marks the task complete when iterations are exhausted. The survivable agent has all 3 stop classes, and the coordinator knows what done actually means. The naive agent has no checkpointing. When its context fills at hour 2, it restarts from 0. The survivable agent saves state at the threshold and resumes in 5 minutes. The naive agent swallows tool errors. Its output looks complete. The survivable agent surfaces errors, adapts, and returns an honest account of what it verified and what it could not. The naive agent has maximal permissions. Any ambiguous instruction at the edge of its task scope produces a decision with maximal blast radius. The survivable agent has minimal footprint. The worst case of any mistake is contained. Experienced Claude Code users in recent research do not micro-approve every action. Their interrupt rate actually goes up with experience, not because the agent is less reliable, but because the interventions are sharper. They let the agent run, and they intervene strategically when the agent surfaces a decision point. That is the relationship this architecture is designed for. Not constant supervision, not full autonomy. Autonomy that earns trust incrementally. Because when the agent hits a problem, it surfaces it. When context fills, it saves state. When it stops for a reason it can explain. That is the survivable autonomous agent. 3 patterns, 4 design decisions, 1 viable production deployment. If this gave you a pattern you can use, subscribe. New episodes every week on Building with Claude. Next, retrieval augmented generation for AI agents, when to use RAG when long context wins, and how to wire a retrieval pipeline that actually improves your agent's answers.